We're going to have a couple of great talks. The first one is on computing asymptotic bounds for small roots and Coppersmith's methods via sum sets. We have Ansong Feng to give the talk, and this is joint work with Hengyi Luo, Kuyan Chen, Abdurrahman Nitaj, and Yanbin Pan.
Yeah. Hello everyone, I'm Yanzong Feng, from AMSS. Now I'm waiting the Mark Aarhus, and this work is with people from AMSS and Normandy University. It's about the Coppersmith method, how to computing the successful condition about the Coppersmith method. Okay. Coppersmith method is to solve the to find the small root of polynomial equation very efficiently. For example, suppose we have a RC modulus n, and p is a unknown prime factor, maybe n to 1/2. Using Coppersmith method, we can find all root with x less than n to a false in polynomial time. How it related to crypto? Suppose we know some most significant bits of P, which is in shadow, and the unknown part is P tilde less than n to 1/4. So we set the unknown part bits as x, which is unknown. So using this result, we can know if we know half most significant bits of n, OP, we can factor this RSA modulus in polynomial time. And why here is 1/4, not 1/5, not 1/6, even not 1/2. That's how Coppersmith method works. Okay, our goal is to find a small root x, and we set the upper bound of x, capital X, which equals to n/1/4. Oh, okay. Next. The first step is to construct some polynomial which shares the same root as x plus m. For example, x to j times x plus m to m, which we can see that they share the same root x0, modular p to m. And the second step is yeah. What's my m is a known constant. Yeah, there's a constant term. Yeah. In this example, in our example is the known top bits, yeah, which is m, and the unknown part is x. So x plus m is the whole p, which equal to 0 when you model p. Yeah. So how Coppersmith method works, the first step is to construct some polynomial which shares the same roots with x plus m when model p to M. And the second step is to use the coefficient vector of this polynomial to construct a lattice. For example, like for this polynomial, the coefficient is nm, nx, 0, 0. We use this as a basis to construct a lattice here. And we want to find a shorter vector VH. Here we use 3L, which is polynomial time. We find a VH here. And from VH, we can compute a related polynomial H. Because like each row is a polynomial which shares the same roots, which equal to 0 when modular P2M. So here, HX is also equal to 0 when modular P2M. And now we know like H has a small norm. Like like when H less than P2M, H should be 0. So if the norm of Hx is small enough, so it would be hold that AH equal to 0 over Z. The condition that's what we call the successful condition of Copps-Smith method, which is like a determinant L should be less than P2M times dimension L. Because what I want to say is like we have an upper bound on the determinant, because if the determinant L is small, the shorter vector of this lattice is small. Yeah. So if we want to know the successful condition of Copps-Smith method, we need to compute the dimension determinant. That's how we get the 1/4. Nice. But sometimes it's not easy. Look, like here, for example, like people use like a 4-fold sum. Yeah, and also like some like for this example is like one paper from Asia Crypt. People like it's not easy to compute in the using the 4-fold sum or like even 5-fold sum. People here like they split the dimension into small part and they compute each part like very carefully. You can see like use many pages to compute the dimension and determinant. Yeah, like but here like I will introduce a very beautiful and powerful tool from like additive combination. Like the credit should be given this to like mathematical person. Yeah. To be honest, like here I prove a theorem like in combination, but we found it was proven in like 60 years ago. I mean, when we submit this work to Stock, we haven't realized we prove a result proven by the first person, like in 60 years ago. Yeah, but it always happens. Yeah. Okay, I know many people don't know like not familiar with Copps-Smith method, but like here doesn't matter. Like I will give a pure mathematical description about this problem. Now consider like A and B, capital A and capital B, they are set from the they are set in the CK. Now we can define the Minkowski sum over CK, which equals like A plus B is the set of small a plus small b. From then like we can define like A plus A, which is like 2A, A plus A plus A, which is 3A, and also like 4A and also MA. And the problem here is like given A, we want to compute the limit, the size of MA over M2K. Okay, how it related to the dimension? Like look, if we want to use Copps-Smith method here, like over this F, we can map like each monomial to the point of C3. That's a map like from monomial to the that point. And now like the dimension of Copps-Smith method. Now the dimension of Copps-Smith method on this F is limit over AF. I mean that's why we are considered as this limit. Okay, now like I will give an example. Like this is A, like which has 3.0001 and 10 in C2. Okay, if we want to compute the limit like the trivial way, the first method is like a manual calculation. We want to compute MA like by manual calculation. Like now MA is the set of IJ, I plus J less than M, and the set of MA is like 1/2 m squared plus something, and the limit should be 1/2. But like when the size of A like becomes larger, or like the dimension of A, I mean like the dimension of A is K. In this example is 2, but when K becomes larger, it's horrible. Like for example, for this A is not easy to compute. I mean, in Asia crypto, like they use like as I show, like they use several pages to compute this limit. But like people in crypto community, like they want to know how to compute. There are some like a heuristic approach from people in previous work, like Asia Crypto 23 and Indian Crypto 24, and also like Euro Crypto 25. Kinjin, he also have some heuristic approach, but it's slightly different from these two, so we'll omit it here. Their heuristic is like if sharp MA, the size of MA is a polynomial in M, polynomial with degree K in M. So it should be like easier to compute the limit. Like we can use computer to compute like we can use computer or like a personal laptop to compute sharp MA in small m, and then like a Lagrange interpolation. Okay, now like it seems everything is done. It's like easy. It's like we can use computer to help us to compute the limit. But how about like does this heuristic true? Okay. Sorry, it's not true. Like we can have some easy counter example. Like for A equals to 0, 1, 5. I mean, from their heuristic, sharp MA should be like linear in M. But like from this figure, we can see like it's not. So I think people shouldn't use like a heuristic approach to compute like Copper-Smith method bound. But that matter. Now like this is the result of our result. Like we prove like the limit is an integral. So it has some like geometry things behind the limit. And in our example, like when A equals to 0, 0, 0, 1, 1, 0, the convex hull is the triangle with 3 points 0, 0, 0, 1, 1, 0. So the integral should be 1/2. Because the area of this triangle is 1/2. Okay. Now compare with manual calculation. When A is like a 0, 0, 0, 1, 1, 0, the manual calculation is computed like a twofold sum. And but if you use our result, it's like integral over NA, which is like 1/2. So it's easy. And also like you can use computer to help us to do this, because like we can use A as the input. We can use A as the input and ask computer to compute this integral. And for the time complexity is like a sharp P. But we also have like a polynomial time approximation algorithm. Okay, now we already compute the dimension of this lattice, and we need to compute the determinant of lattice. Okay. This inequality is our result. Okay. The determinant is like we can write the determinant as x1 to p1 times blah blah times xt to pk and times n to pf. So we want to compute like pj and pf. Pj is a summation over ij, and pf is a very changed thing in this paper. Pf is the sum of sharp ga. And we also have some similar result on the determinant. For pg, we can prove pj is an integral over ig. I think this paper is, we use some results from one paper accepted by JAMA, which is a top journal mathematics. What's the name? Yeah, maybe Annals, maybe J Journal America Society, something. And for PF is a very changed things. But like we have a co-author from mathematics. He worked on additive combination, and he gave a very beautiful construction. He constructed A tilde F, and also we can prove PF here is like M sharp MA minus sharp MA tilde. So the leading coefficient of PIF here is like the integral over A minus the integral over A tilde. So that's what I want to say, like a polytope is all you need. And in practice, like it's very computer friendly for input. If we want to use Coppersmith method to compute some specific f, we just use monomials of f as input to give them into computer, and the computer will help us to compute this integral, and the temperature capacity is P. Yeah, that's all. Thank you.
When I speak of how one-dimensional this case,
yeah,
I think things to work there. So suppose that you have a set which consists of number A
yeah,
and the multiple of A. Then the only sums you can get are the multiples of A. On the other hand, if you take the number A and the multiple of A minus 1, which are relatively prime, you make many more combinations. But the convex hull,
yeah,
the number A and 100A or 100A minus 1, the convex hull is also the same. So how can you, the number of possible sums depends on whether the numbers are multiple other in one dimension or they are relatively prime. But the convex hull, the size of the convex hull, does not seem to depend at all on.
It just depends on A, not depends on the M.
So why does my counterexample not work?
Let's come back. Let's.
With prime numbers, the number of combinations is much larger.
Yeah.
If the two numbers are multiple.
So what's going on?
Okay, you might understand, like you are asking if if M1 is a multiple of M2.
Then the number of combinations is way smaller than if the two numbers in the set A are relatively prime to each other. But your calculation based on the convex hull does not take into account the multiplicative properties within A, within the set A. It's only taking into account the convex hull in one dimension, the difference between the smallest and the largest.
Sorry,
okay, let's take it.
Later.
More questions? Okay.